Yeah, so let's get going. Um, the previous class, we looked at the purpose of shells and beams, both from a practical point of view as well as the advantages in a modeling point of view. So now we'll go into some specific names for these shells and also the beams as they are used in the case of flight vehicle structures. So some of you with a aerospace background may already be familiar with this, but this is especially for those who are new to the aerospace background. So we already saw that the semi-monocoque construction is the one which is most preferred for a lot of aircraft, a very large class of aircraft today, because most aircraft you would want it to fly faster and take more payload, and the most efficient option there compared to truss and monocoque constructions is the semi-monocoque construction, which is what we saw last time. So now let's look at what are these elements and which of those are shells and beams in this particular slide. So we can broadly look at the aircraft to be made out of two parts. One is the fuselage part, the other is the aerodynamic surfaces that includes both the wing as well as the stabilizers. So it's been conventional to call them as horizontal stabilizer and vertical stabilizer, though these are terms which are associated with the ground level, and when the aircraft actually is flying, it could be in very many different orientations. We continue to call them horizontal tail and vertical tail, but essentially what they are is the horizontal tail is actually a pitching stabilizer, and similarly the vertical tail is a yawing stabilizer, right? So, the corresponding control surfaces, of course, the elevator and the rudder, and sometimes you could also have a situation of an all-moving tail, in which case the entire tail or the entire stabilizer also becomes the control surface. So whatever those kinds of cases might be, typically you can think of these two broad categories in which you can divide the overall aircraft structure, and many other flight vehicle structures also get into this. For example, a helicopter rotor blade, you can think of somewhat similar to this, but there are subtle differences, and we'll touch upon them as and when it's essential. Coming to each one of these, in both the cases, you are going for the semi-monocoque construction. As you can see in this skeletal picture over there in the cross section, when you cut, you have a shell-like structure, which is essentially your cover skin in both the cases. One case, it is typically oval in shape. In the other case, it's the airfoil cross section in shape. And in addition to that, there are other shell-like surfaces which are especially in the case of the aerodynamic surfaces, especially if they are large thickness, you would have the web of the spars, which are also like plate-like structures. So essentially, they are also something that can be treated as shells or plates. Now, in addition, you have the second kind of reinforcement, which we saw was essential when we moved to situations where the loads are large, and therefore the thickness of the skin which is required to handle such a load becomes humongous. So we went into these beam-like stiffeners. Now, the beam-like stiffeners, again, they can be classified into two parts. One is essentially what we call as the longitudinal stiffeners. The other are the transverse stiffeners. By longitude, we mean the direction along which the dimension is much larger compared to the other, because already we saw this could be treated as a overhung, simply supported beam as a whole, the entire fuselage, and the entire wing surfaces typically can be considered as a cantilever kind of a beam configuration. So in either case, you have within that, you could have along the length, you could have what are known as spars, and especially in the case of the aerodynamic surfaces, the corresponding thing in the case of the fuselage becomes what are known as the longerons. And similarly, you would have, in addition to the spars, which are the primary longitudinal stiffeners, you have the stringers, what you see over here, those small things, and then over here also you typically have stringers, right? Now, these are sometimes interchangeably used. Sometimes, though in the initial stages, longerons was used primarily to refer to the longitudinal stiffness in the case of the fuselage. Sometimes people do in the different parts of the industry refer to some of these stringers also as longerons. Essentially, the difference between longerons and stringers is that longerons are much longer, as the name itself suggests, and typically they would be running almost end to end, though it's not exactly end to end because the ends have certain specific requirements. Therefore, it will be close to the end of the, let's say, the nose of the fuselage to the tail cone end of the empennage that you have. So in that case, it will be right from the fuselage, or if it's a continuous tail, right to the center line of the fuselage to the wing tip that you might have. Typically in the wing tips might be curved, etc. Therefore, the longerons may not actually many a times run all through, and moreover, anyway, the stresses there are much lower at the close to the wing tip, or for that matter, close to the nose cone and or the tail cone tips, except when there could be an impact load, for example, at the nose cone, etc. So those are special cases, but you're talking of the regular flight loads over here. So longitudinal are of two kinds. Then in addition, you have what are known as the transverse stiffeners. So these are terms that you will keep coming across every now and then. So longitudinal and transverse in many different contexts. So it's important to remember that the longitudinal is along the longer directions where the dimensions are much larger, and the transverse are along the smaller dimensions. So we in fact visited this in a different context when we were distinguishing shear stresses and strains between the in-plane shear stresses and strains on the one hand and the transverse shear stresses and strains. So there also we saw, for example, if it's a plate-like structure, the stresses along the thickness, which is a smaller dimension, in this case were called as transverse. Similarly, here also the components which are stiffening in the transverse direction are the transverse stiffeners, and typically in the case of the aerodynamic surfaces, you would call them as ribs, and in the case of the fuselage, you typically call them as frames. Sometimes they could be what are known as formers, and sometimes they could take the form of what are known as bulkheads, which are much larger. So typically, you would have pressure bulkheads at the front and the back, and in between where major structures are joining, be it the empennage or the wing in particular, you would have cross sections of the frames which are much, much larger. Sometimes they are also referred to as bulkheads. So this is something that you need to be kind of familiar with, because depending upon whom you're talking to, and specific industry also depends on the region in which they operate, and certain certifying agencies with which they are commonly associated with, there could be a slight interchange of terminology, but overall this is what exists. Another term which is used for the transverse stiffeners is the rings, because they take the form of a ring-like shape, especially in the fuselage. So that's what you typically call them. So now we will visit each one of these four categories. One is the shell-like structure, namely the cover skin. Though as I said, the webs of the spars, front and rear, and if you have multiple spars, those as well, would typically form shell-like structures. We will keep them separate for now as a part of the spar itself and treat the whole spar as a beam, where you can think of the spar caps to be functioning very similar to the stringers, and the spar web, which is essentially functioning as a shear carrying member. So that is the primary distinguishing factor of either the cover skin or the spar web, is that they are shell-like structures, and shell-like structures are very good at taking the shear. So in fact, many of them might be named after their shear carrying capability itself. So, and that shear that we are talking about there is actually the in-plane shear. It's not the transverse shear. The transverse shear is typically a higher order effect compared to the in-plane shear. And transverse shear is important to be considered when you're trying to analyze the failure or try to avoid or delay the failure. So those situations, understanding the transverse shear becomes very, very critical, but in many other situations, it's the in-plane shear which is predominant. Coming from the beam perspective of the entire wing, the shear that is carried by the spar webs is actually a transverse shear. But if you look at that alone as a plate or a shell, that is essentially the height of the spar web and the length between two transverse ribs that you have, that is essentially like a plate. And for it, what we are talking about as coming from the lift distribution, let us say, is essentially an in-plane shear as far as that is concerned. But when you're looking at the beam as a whole, yes, it is a transverse shear. When you're considering the entire wing as a beam, then you're essentially talking of it as a transverse shear. But if you're breaking it up further into smaller parts and looking at each one of them as separate individual beams and plates and or shells, then it becomes an in-plane shear. So typically, those kinds of components which have a dimension which is very small, namely the thickness compared to the other two dimensions, length and breadth, their primary job is usually the in-plane shear carrying capability. Yes, the skin also carries quite some axial load coming from the bending, etc., but it shares that job along with the stringers and the spar caps, which do a phenomenal job themselves. And even when the skin fails, for example, in compression, you know that the rest can take the load. So in that sense, yes, we are having a so-called stressed skin concept, but the primary stress that they are required to carry is usually the in-plane shear and part of the axial loads, which are also in plane normal stresses and strains. Now, I think that kind of sets the background for this. Let's start with the cover skin now. So let's look at the functions of the cover skin one by one. So as I said, and some of these might be valid for the spar webs as well. Yes? Mm-hmm.
For example, we have ISAB, Indian Standard Heavyweight Beams,
Mm-hmm.
okay, which that is mentioned in catalog for Indian Standard codes for Indian Railways. Do these eye sections or any sort of section, the metal section, what we use here, do they have that kind of catalog? Because it's necessary for the certification of that aircraft.
Right. Yeah. So as I was mentioning earlier, there are regional certifications that are involved. The FAA in the American region, and you typically have the
British also DCA.
Right. So and Europe has its own regulation. Similarly, in India, we have the DGCA for the civil and the CEMILAC for the military aircraft. But what has happened is in earlier years, they used to go into the details like what you're talking about for the Indian Railways, the way it is specified, the beam in terms of dimensions, etc. Now, slowly, all of these certifying agencies, they're moving towards a different paradigm where they don't go into the specification of these details, but in terms of the requirements in a qualitative sense. So, because there is so much of difference between one kind of situation and another, starting all the way from, let's say, large aircraft for transport to military aircraft, again within them so many different categories as we saw the classifications earlier, helicopters, and then again you have so many classifications based on the size, based on the speeds at which they fly, etc. So the actual numerical or quantitative requirements could be quite different for each one of them. Even if you take just the flight envelope, for example, the maximum load factors for an acrobatic aircraft would be very different from that of a transport aircraft and various other categories as well. So keeping that in mind, there are certain things which are specified quantitatively also, but we don't go into as much detail like, for example, specifying the eye section in terms of what is the width and what is the ratio of the width to the thickness that you should have, etc. This is usually the prerogative of the companies, because you know that it's pretty much, it used to be a monopoly with Boeing to start with for transport aircraft. Then Airbus came in. and now it's kind of a duopoly, at least at that size of aircraft. There are many other players in China, Brazil, Indonesia, etc. And all of these typically have their own in-house developed certain design principles, certain design procedures, and based on what has worked for them in their previous aircraft, they kind of carry over. Of course, they innovate and try to make things better as they start using newer and newer materials. For example, earlier they were using only aluminum alloys, a few other metallic alloys. Now they're moving into composites, so they might bring in some of those things. But whatever that is, eventually it has to satisfy certain overall requirements that the certifying agencies provide. Yeah.
So one more thing,
Yeah.
for design perspective, do we consider any strength of the skin or it is not taken into consideration?
For the design, do we take this skin strength into consideration? Yes, we do, because it's a stress skin. So depends on which side. So if it's a tensile side, the skin is supposed to continue offering throughout the loading process, because failure for it would mean material failure, which is not allowed in the normal operating sense. But on the compression side, you have to ensure that when the skin is operating, fine, but when the skin has buckled, in the post-buckle behavior, also it is able to handle it along with the rest of the elements that are there. So in other words, you are essentially on the compression side, which is the top surface of the wing, you are designing the spar caps and the stringers there to pretty much take the entire load. So in the case where all of the skin panels are, let's say, buckled. So you have, that is the design requirement as far as the top stiffeners, longitudinal stiffeners are concerned. Yeah. Anybody else? Any questions? Okay. So coming to the cover skin, so as I said, it is essentially a shell-like structure, and for this, the primary load which is coming, the external load that is coming is the air loads, and that includes the aerodynamic pressure to the stiffeners. And as I was talking in an earlier different context, if this is a plate which is like a panel of the wing, then the pressure loads that are coming are the direct resistance, though is the thickness direction normal stress, that is much smaller compared to the bending stresses that develop, which are also normal stresses. So sigma 11 and or sigma 22 can be much larger compared to sigma 33 if x3 is the direction of the thickness. So that is one of the things. In addition, because of the skin friction, you would have shear stresses which are developing in the boundary layer, and that has to be balanced by this. So that shear stress that is there is a transverse shear stress, because it's parallel to the surface, fine, but it is having a component, complementary component, which is coming over here. Because if there is a stress like this, this is essentially 3-2, and there will therefore be a 2-3, which is essentially a transverse shear stress. But the primary thing that they are resisting is because of the bending, and that is essentially your sigma 11 if x1 is along the direction of the length of this particular beam, which is the wing. So it transmits the aerodynamic pressure to obviously to whoever it is connected to, you mean in the immediate sense. So at the transverse ribs will not be there at all locations. So at certain lengths, everywhere you would have the stringers going along. So the first point of contact, and of course the spar caps as well, it would be transferring the that load to them. Or in other words, you can think of each between two adjacent longitudinal stiffeners, be they spar cap and a stringer, or between two stringers. It's essentially like a panel which is having certain boundary conditions based on how this attachment is done, and the other boundary condition along the length would be where the transverse ribs are essentially attached. So it becomes essentially a panel like that. So first thing that it does is to transmit this aerodynamic pressure to the stiffeners, be it the spar caps or the stringers. The next thing is it resists the torque and shear forces along with the shear web. So for example, if you look at this particular box, or even with the leading edge, or with the trailing edge, you would see there is a box like this. So these are like thin-walled boxes, and therefore closed cross sections which are very good at taking the torque. The torque could be coming from the pitching moment which is acting on the aircraft wing. It could also be coming from the so-called concentrated loads, which are essentially high intensity loads as we saw earlier, coming from the engine weight, engine thrust, and other such concentrated loads. So maybe the control surfaces. So the control surface essentially, when it deflects, it's essentially causing torque for the wing as a whole. So that torque has to be resisted by these boxes. So typically if there's a total torque of T, let's say in this particular case, you could think of it as T1 plus T2 plus T3 is essentially balancing that. So T1 is being taken by this, T2 is being taken by this, T3 is being taken by this. But between these two boxes, you have a common wall. So the shear stresses in those will be in opposite directions. So an algebraic sum is what that has to cater to. So that is how the typical sizing of that will be arrived at. In terms of sizing, there are two aspects to it. One is because it's a plate or a shell-like structure, you have the in-plane dimensions. As far as the height is concerned, it's kind of limited by what your aerodynamicist has designed the airfoil as based on the particular chord and the thickness to chord ratio, and where you are locating this spar, the height is kind of defined. But the width depends on how you space these ribs. So how far you space these ribs, so that's what it depends upon. The primary thing that you're doing is in terms of choosing the material or materials if it's a hybrid design, and the total thickness of that and the thickness distribution in the case of a hybrid design.
So
What is that?
shear-web?
Shear-web. So this is essentially what we are talking about over here. It's a web. So for the I section, we call this as the flanges and this as the web. So because the web is primarily taking shear, so it's a common terminology used in the industry to call it as the shear web. Right? So that shear web is taking the shear coming from the torque, as we just discussed, from the T1 and the T2. The difference in the shear stress due to both of them, essentially the algebraic sum, is what it's taking. In addition, it's also taking the transverse shear coming from the lift distribution. Similarly, if you look at any panel which is on the cover skin on the top or the bottom, they are taking, of course, let's say in this case, the T2 that was there, the torque. In addition, they are also taking, because of the drag, there is a transverse shear which is coming. So one of the shear is essentially associated with torque, the other is associated with bending, because the bending loads which are there are not as pure moments, they're not pure bending moments, they are coming from a load distribution, which is essentially the pressure distribution and or the shear distribution due to skin friction. Now those are going to be causing, in addition to bending, which is their primary effect, they are going to cause a secondary effect, which is the transverse effect. Now, as far as the structural element is concerned, it is blind to whether that stress is coming from the torque or is it coming from the shear, which is due to the transverse loads, namely the lift distribution in this particular case. So that also gets algebraically added to that, and essentially when you're designing this, that is essentially sizing it for thickness and or choice of material, you have to take into account the most critical case when the maximum torque and the lift distribution are simultaneously present, and how each of them algebraically add or subtract, and in different phases of flight how they will change, and you have to take the most critical case and essentially size it to be able to handle that. Yeah. The third and final thing I'd like to mention about the cover skin is that it enhances the axial and bending stiffness, which is provided by the longerons. So in the case of the fuselage, you have these things which are running all through, or in the case of the wings or the other aerodynamic surfaces as well, you have these spars and their spar caps which are there, which are the flanges of the I section or something similar to an I section. Now, those are the ones which are primarily handling the bending which is coming from the lift distribution and or drag distribution. But in addition, the skin can also enhance that bending stiffness because it has a finite area. In fact, though the thickness might be small, it's running all through, so it has a substantial area to offer. It's almost the same distance, or in fact slightly higher distance from the neutral axis. For all practical purposes, it's the same distance because the structures that we are considering are all fairly small in cross-section geometry, and therefore the sizing of the stringers, etc. So it's almost at the same distance, but the area is fairly large because of the large length that is involved of the cover skin, both at the top as well as the bottom. So when we are calculating the bending stiffness in the simplest way, let's say EI, considering all of these are made out of the same material of the same Young's modulus E, then when you're calculating I, you can very easily see that if this is the neutral axis, you're essentially taking the areas multiplied by the distance from the neutral axis squared. So you can quite easily see that it's not only the spar caps and the stringers which are contributing to that I, almost the same order of magnitude term will be contributed by the skin as well. That has to be taken into account. But with the catch that for the top skin, when under flight, you will have compression, and therefore there is a possibility of buckling, and most of these are designed for buckling, in which case you have to design just the stringers and the spar caps for being able to handle that load, even when the skin has buckled. So that is essentially what you're talking about. There will be a certain small amount which will be handled by the skin. Those depend on the post-buckling equations, but primarily you typically design the overall cross-sectional area for the top stringers and spars so that they can handle the entire bending loads coming from the lift distribution in the most critical case as far as the flight envelope is concerned. Very good. Yeah, yeah, absolutely, absolutely. So we'll go one by one. So when we look at the transverse ribs, we will see that that is one of their primary functions. You're essentially reducing the overall length, because even for a typical column like you have like this, it depends on the boundary conditions, of course, but it's proportional to the bending stiffness and inversely proportional to the length of the column, right, squared. So it has a huge effect, just like the moment of inertia has that square term coming from the distance, how far it is from the neutral axis. Similarly, this distance also, the length of the column, plays a very critical role, and that length is determined by the spacing or the pitch of the transverse ribs. That's right. Anybody else? Any questions as far as the skin is concerned?
So in general, when the skin has a local buckling phenomenon, and most of the load is actually transferred through pressure. So how do we actually account for the actual load that comes? Because part of the skin is probably not going to be stiff enough to take that pressure. So how does the load come into factor in that case?
Yeah, so essentially what's happening is that it's not able to take this pressure. Even when it has buckled, in the post-buckling scenario, it can still take the, so the pressure load. It's just transferring that load to the rest of the structure that is there, okay? But it's good that you brought up that point, because there's another place where that comes into picture in the fuselage, because you have internal pressurization. So there is no question of buckling that is happening, even though in terms of the loads which are coming because of that hanging thing that you have on either side, that is essentially undergoing bending. So there are small portions which are undergoing compression, but you rarely design that for the post-buckling kind of a scenario, because they are small regions, and in any case you will not save too much of a weight in most of those kinds of situations, okay? But the internal pressurization is going to offer the hoop stress and the longitudinal stress, which are going to be relieving stresses for that compressive load. So you typically have very low compressive loads that the skin is dealing with in this particular case compared to the wing.
So also in the post-buckling case, probably the shape of the longerons is going to change, or at least the position of it. So then when we convert the loading that is coming into the skin pressure
right, 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 right. A very good point there. But typically, you see that the frame that you can think of, which is formed by the spars and the stringers, is much stiffer compared to the skin. So yes, there will be a small change. It's not non-zero. It is not zero, but the effect is a very higher order effect in terms of how the spacing could change even after the post-buckling has happened. So post-buckling, what would typically happen is that there will be some kind of a curvature that is developing over there. And because these are placed so close to each other, they may not affect even the overall airfoil shape. So it all depends upon how you're designing the spacing of the ribs and the stringers and the panels which are allowed to kind of buckle. So it's typically the top surface which is allowed to buckle. It's the bottom surface which is usually kind of almost like a plate in many airfoil configurations. Since the top is essentially already curved, okay? So now that curvature is changing by a small amount, and typically that is also addressed for not only from a structural point of view but from an aerodynamic point of view also, because there's a small change in your airfoil configuration. So what is done is, there are different phases of flight, and the cruise is the one which is going to be dominant. So typically you know that in cruise what kind of loads are going to come, and therefore what kind of post-buckling scenarios might come. So you work backwards to make sure that the airfoil shape that what you want to have is such that even after post-buckling it arrives at that optimal shape. Right? And for the other regions, it's actually operating at slightly suboptimal kind of configuration. So, so this is kind of, you're trying to work backwards. You know what's going to happen because of the post-buckling, and therefore think about it early enough to make sure that in the unloaded situation, it is not the actual airfoil that you want. It's slightly different from that, so that once post-buckling happens, it becomes the actual airfoil kind of a cross section. So these are all kind of nitty-gritties which typically people get into only in the detailed design stage. So in the preliminary design stage, people usually will not bother about these things because many of these are higher order effects. Yeah. So anybody else, any questions? Okay, so let's move on. So next, let's talk about one of the stiffeners, beam-like stiffener, which is essentially your stringer, because once you deal with this, the spar-cap becomes very easy to deal with because it's just an amplified effect of whatever we talk about in the case of the stringers. So again, the distinction between these two, as I said, in most scenarios is that these are much shorter, these are much longer. So for example, when these are running along the fuselage, there might be certain windows which are coming up, because of which the stringer might have to be cut at that particular location. Instead, a doubler, which is typically used, is frame around the window. The same thing is the case for access panels for maintenance and or certain supplies that you want to give, the fuel supply and or the cargo loading, etc. So depending on all that, you have many different access panels, primarily for maintenance purposes, and all of them, just like the windows, will have certain frame around them, so that the stress distribution around them happens appropriately without causing any stress concentrations in between. So as far as the stringers or longerons are concerned, the primary thing, whether it is in the aerodynamic surface or in the fuselage, is to resist the loads which are in the which are normal loads with normal stresses, which are coming either from axial loads, which is especially true in the case of helicopter rotor blades where centrifugal forces are large, but most of the fixed wing aircraft, it is primarily coming from the bending loads which are occurring both due to the aerodynamic forces, lift distribution, as well as the so-called concentrated loads coming from the engine control surfaces, etc. But the bending loads, as you know, the stress, that is the dominant stress coming out of it, is an axial stress, and therefore this is able to take. Now, though we say it's taking bending, remember one thing to remember is that each of them is not undergoing bending by itself. It's acting as a combination of the top stringers with the bottom stringers. The top stringers are all undergoing compression in the flight, and the bottom are all undergoing tension. So together they counteract the bending loads which are coming from the lift distribution. Next, as you pointed out, you were talking about the transverse ribs. The same thing is in the case of the stringers as well. In terms of the spacing that you have, it increases the buckling strength of the skin, because there we are talking of not only the column buckling but also panel buckling, in which case both the dimensions of the panel matter. But of course the main compressive load is the one which is coming over here. So in terms of a column length or a panel length that is of more significance, it's essentially that which affects. But this direction also can change your post buckling behavior quite a bit, and so this spacing has to take into consideration the buckling of the skin and its post buckling behavior as well. Next, very important point is that suppose there is a crack which develops. Now let's say there is a crack which is developing like this, then you can see that if there were no stringers at all, that crack would grow very easily. But once you have a stringer, it's like a bridge that is there. Now it's a stiffer region. It has to go around that. Either it has to go through the whatever the joints that are there, could be the adhesive joint and or the riveted joints. Then it has to essentially get delayed in terms of the crack growth, and which is an advantage in terms of how you go about the overall design process. Now, in addition to that, it arrests crack growth in the skin by taking the excess axial tension as well. So for example, if it's this tension that we are talking about, now once the skin has cracked, that particular region, the skin will no longer be able to take the tension. So that additional tension which was earlier taken by the skin is now distributed between the two adjacent stringers. So it's taking, one is it's delaying the growth of the crack. The second is that it's redistributing the load such that the stringers will take additional load which the skin was already taking. So this is typically what is something to be considered on the tension side rather than the compression side, where we are predominantly worried more about buckling, which usually happens much before the material failure happens. So it's here where the tensile loads are predominantly there, that the tension of the skin which has cracked will be shared between two adjacent stringers. Yeah, so as I said, the spars essentially are an amplified version of the stringers, especially when you're talking of the spar caps. So it does the same thing. The reason it's amplified is you can very easily see that the cross-sectional area of this is much larger compared to the cross-sectional area of a typical stringer, and therefore it also is taking an axial load. The top spar cap or flange is taking a compressive load. The bottom spar cap or flange is taking a tensile load. Together they are essentially resisting the bending predominantly coming from the lift distribution. The second thing is, of course, the spar is not only the cap or the flange but also the web, what we called as the shear web earlier. So the web resists the shear coming both due to the torsion as well as the transverse loads, which are the shear forces along with, of course, the skin. The skin also contributes to that. So for example, the drag that is there, you can very easily see that you are having this particular direction, you are having the shear stresses which will be taken only by the cover skin. But when you're coming to the lift distribution, you have not only the skin handling that, but also the spar caps, and in fact a very large fraction of that load, which is the transverse shear load coming from the lift distribution, will be handled by the spar caps. Okay, now let's get on to the transverse frames or ribs. The primary function is for it to maintain the cross-sectional shape. So because it's essentially taking the same shape as the airfoil cross-section and placing it at certain regular intervals, you are making sure that the skin, even after it deforms, it doesn't change its shape too much. So this also helps in the question that you asked in terms of the post buckling. So huge effect is essentially in terms of the transverse ribs trying to maintain that shape, which is why sometimes they are also called as formers, especially in the case of the fuselage. Apart from maintaining the cross-section shape, they also are typically placed in such locations where, let's say, the engine is attached to the wing, or let's say the wing is attached to the fuselage, or tail is attached to the fuselage. So in all those locations, you can very clearly see that there can be high intensity loads, what we call as concentrated loads, and these need to be diffused appropriately into the skin. So though the load itself might come from outside through the skin, by the way in which these are attached to the skin, there is a very easy way in which overall load is kind of distributed, which is what we call as a diffusion process. So essentially at that diffusion, make sure that there are no stress concentrations, or even if they do occur, they are not too much of an issue. Then the third thing is that it redistributes the stresses around structural discontinuity. So when there is, let's say, a wing tip, for example, or let's say a change in the wing sweep at some location, or let's say the circular cross-section of a fuselage at some locations attached to a cone. So there are structural discontinuities at those locations. So typically you will find formers and or ribs at those locations. These are the transverse stiffeners, which make sure that at those kinds of, so one is there is a load discontinuity because of a so-called concentrated load. The other is because there is a geometrical discontinuity, which is essentially coming from the structure changing its shape and or size suddenly. So therefore, you would want to ensure that those are taken care of by appropriate transverse stiffening members. So then the other thing is what you were talking about earlier, increasing the buckling strength of the stringers and the skin. So it's not only of the skin, but also of the stringers, because their buckling is also taken care of by the actual spacing of the transverse ribs. And finally, it helps the skin to take the hoop stress, and this is especially important in the case of the fuselage, where there is an internal pressurization, and therefore the hoop stress can be one of the dominant loads based on which the skin thickness is decided. So the kind of skin thickness you might have arrived at if there were no transverse frames would be much larger compared to because of the presence of these transverse stiffeners and the way they are almost rigidly attached to the skin. Therefore, you can have lower thickness in the skin compared to when they were not there. Okay, so I think this is the end of this slide. So any questions on this before we proceed further? Yeah.
Most of the aircraft store the fuel in the wings.
Mm-hmm.
And there are some aircraft designs which have pressurized tanks in the wings also.
Mm-hmm.
So will that have an effect on the design of the wing?
Very important question, valid question. So typically you see that when you're storing the fuel, and you also have these compartments that are created by the transverse frames. So the transverse frames usually will not be solid, like in the case of the pressure bulkhead, for example. They will not be solid. They will be frames which will have cutouts or openings, and typically you will have these in bladders, and those bladders will then be the pipelines. The fuel lines will be connected, and they will be going through those cutouts. So the fuel, how you want to dispense and how much you want to store in the wing, all of this will also come into the structural design, because that brings in the weight distribution due to the fuel weight. But as I said in an earlier class, that's essentially a relief. So because it's bending in the opposite direction in flight, and therefore it's actually an advantage that you're having, but you have to take care of that, take note of that advantage, and take that into account while sizing, so that you're not over designing or having a more thickness than required. You take advantage of that. But you also have a situation that you have to design it for the minimum fuel kind of a configuration, where there's hardly any fuel in the wing, or especially if there's also fuel in the fuselage as well. So you have to make sure that those kind of considerations are also taken into account, and or you have to devise the flight plans in such a way that such eventualities when they occur, the kind of maneuvers and or other things which are performed, there are certain things which are not allowed and things like that. So as long as you take all that into account, this compartmentalization works. But fuel is not the only thing you're going to be handling there. You also have the control surfaces which are attached, and therefore the control lines, be it a fly-by-wire system in which the electric lines and or the pneumatic and or hydraulic servo lines that are running, they would also be running through these transverse frames, and those cutouts help with that as well. Anybody else? Yeah.
Mechanism usually when there is like a transverse rib and there is a spar or longeron passing. So is it that generally in the transverse rib there is a recess provided, or is that?
Yeah. So it's typically, just like there is a cutout in between, there are also cutouts at the edges which allow for these stringers to pass through them, especially if they're longerons, for example, and of course the spar caps. So they will pass through them, and they will be attached both to the skin as well as to the transverse frames on ribs.
So there will be a riveting done at the location where the spar passes.
That's correct, yeah.
So also how does the rib help take the hoop stress? Because
So what is happening is that you're trying to think of between two adjacent ribs what you have, okay? Now if you didn't have that, the entire cylinder could go up like this. But once you have these transverse stiffeners, they are so stiff that change the diameter at those two locations. So there will be a slight bulge in between that is happening, which will not be as critical as the entire thing moving out, or the entire diameter moving out. So essentially you are trying to take that transverse load, that hoop load that is coming, it is kind of getting redistributed, because remember that those frames are also riveted to the skin, okay? So the hoop stress, just like in this case we were saying that the lift distribution is first coming to the skin and then getting transferred to whatever it is connected to. In this case it's going from inside out instead of outside in. There's a pressure. It might be felt initially by whatever is the first cut thing, and then it's getting transferred to that. So essentially the former along with the skin, cover skin, are essentially sharing that load, and therefore the hoop stress, there is also relief for the skin. So two cases, one where there are no formers, the other where there is a former. You have a better situation for the skin in the case of with formers because of that.
but that will lead to an increase in the maritime stress.
Increase in what stress?
The axle stress. The maritime stress.
Yeah. No, but there also you have stiffeners, right? So you have the stringers which will be taking that load, the hoop, the longitudinal load that is coming. So the transverse stiffeners will not help with that, but your longerons will be helping with that.
No, so like if I have a case where I put a transverse stiffness on
Okay.
a ring,
Uh-huh.
and I am trying to restrict the deformation that particular cylinder is going to have
Hmm.
with the ring, then there should be an increased maritime stress near the ring.
Oh yeah, in between that, yes, that will be there, but that's usually not so much of a problem. First of all, you would have the hoop stress much more compared to the longitudinal stress, typically about almost the double, and the fact that you have these additional stiffening elements that are coming between them, that will take care of that. So you're right that the fact that instead of allowing it to uniformly expand, you're allowing it to bulge. So that will cause a secondary effect, which is essentially a longitudinal stress because of that. Yes, that will be accounted for, but those are typically much smaller terms to be added. And because you have the additional stiffening members, that's not usually an issue. And it's fairly closely spaced in terms of the longerons that you have.
So also in case of the aircraft pressure bulkheads, what is the structural design at where the pressure bulkhead joins the fuselage? Because there is going to be a a hoop stress discontinuity, like if I could assume it's going to be a spherical shape and this is a cylinder,
Yeah.
there's going to be a hoop stress discontinuity where it joins. So in general, what is the structural design that goes in an aircraft?
Yeah, so typically for conventionally it has been mostly bolted design. So you have bolted joints around that where the bulkhead is attached to the cover skin. Okay. So, but these days there's also an additional adhesive layer which is used. I think we discussed this earlier, right? The sealant and other things. Yeah. So that's the direction in which it is moving. But the certifying agencies, in many situations, they still insist on a bolted joint design, especially for the pressure bulkheads.
So even in metals, do we use the adhesive scheme or does it just?
No, it's typically welding or more advanced forms of welding that are available today. Depends on the specific metals that are involved. Yeah.
Talking about the instead of that individual rings, if you provide a helical reinforcement kind of thing, it will provide a better confinement to this entire process.
Helical.
In the sense, one, that it's a kind of a continuous. But
Mm-hmm.
single ring after certain distance, we are doing
Fabrication is
Yeah, yeah, fabrication is an issue. Yeah, but it's good that you brought out that point because that's how the process, logical process is arrived at as far as filament winding is concerned. So when you are doing a composite pressure vessel, typically you build it out of this, and you know the angle. You know the hoop stress is approximately double that of the longitudinal stress. So it's just typically around, I think, 53 or 54 degrees is the direction of the principal stress. So you typically will put your filaments along that direction when you're winding to make sure that, because you know that the performance of the composite is best along the fiber direction. So you put the fiber direction along the maximum principal stress direction. So that way you're taking care of that, and it will go through one loop, and when it's coming back, it will go at minus 54, so that essentially it's taking care of both the directions. Yes, yes, yeah. No, but as you said, in the case of that's as far as filament painting is concerned. So let's not mix these two up. So when you're talking of the formers over here, so essentially what you're saying is that in that kind of a design, it's an ingenious way of combining your transverse stiffeners with the longitudinal stiffeners, because to some extent when you're moving in a helical sense, you're also offering certain longitudinal stiffening that is over there. But as a conceptually, yes, that is a very good idea if it could be worked out appropriately. When it's a pure metallic design, for example, you would have the fabrication and the design process a little more complex. It's not that it's not doable. Today's technologies, you can do it, but it's much more involved compared to the conventional design where it's more like a that you have. But that's a very interesting, ingenious way of going about it. And as I said, that's the same concept which is used in filament winding.
So, but doesn't a structure like that lead to torsion when we go into a long distance? Like if I pull a structure like that, it will actually have torsion because of how the stiffness is.
No, so typically you will have it in both directions. So you will not, yeah, yeah. Yeah, good point. So anybody else? Okay. We have time. Let's go. Okay. So now let's focus on some of them a little more detailed. First, let's start with the transverse members. That is essentially the rings, the bulkheads, the ribs, etc. And as I said, they require certain cutaways, and we'll see the component classification over there. Oops. Okay, I think, okay, so this is the next assignment for you before we get into that topic. So this is based on what we have done so far. Once again, it's more of a literature survey, and in addition to Jane's All the World's Aircraft, there's another useful resource for some of these things, which is flightglobal.net. It's essentially a magazine called Flight International, which used to have a printed version. I don't know if they still have a printed version, but it has a website, flightglobal.net. Some of this data is difficult to get, I understand, but how much ever you can get, you try to get into this. Essentially, we are trying to compare these three different design paradigms that we were talking about earlier, namely the truss-like design, the the monocoque design, and the semi-monocoque design. We already know the kind of aircraft to which it is applicable. The truss type more for the smaller aircraft, very low speed. Then you go to some medium level in terms of speed and payload capability. You go for the monocoque and go to much higher speeds and larger payload carrying capabilities. You go into the semi-monocoque construction. So for each one of those three types, I want you to identify 5 examples. They could be either recreational aircraft, trainer aircraft, it could be passenger aircraft, it could be military aircraft, it could be anything. Essentially, the structural construction principle that is involved is more important for us. And we are focusing primarily on the wing, not on the fuselage. So the wing constructions is what we are looking at. And many of this data is actually proprietary to the companies in terms of the skin thicknesses. But there are a few aircraft, very old aircraft, for which some of this information is available. So you can try to get hold of that. And the primary thing is to see, because we've been talking in a qualitative sense in terms of the sizing and shaping, but there are certain things that it depends upon and certain things it's more sensitive to compared to certain other things. So thing is the wingspan. So the larger the span of the wing, it could be either because you have a larger aircraft or because you're designing the same aircraft with a larger aspect ratio, typically for lower subsonic flights. So then you're essentially seeing how that has an effect in terms of skin thickness that you require. Because for the keeping all other things the same, the larger the span you have, the larger the bending moment arm that you have. But if it's a redistribution that is happening, there might be an ideal situation where you have an optimal aspect ratio that you're dealing with, and therefore the optimal span that you're dealing with. So that's the reason why this will especially be useful if you have some of these examples. You will have essentially 5 plus 5 plus 5, 15 examples over there. Some of them would be of the similar category. Then you can have a comparison and see how this variation, how important it is in terms of making certain design decisions. The other thing is in terms of the overall weight of the aircraft, the maximum takeoff weight, MTOW. So you plot the skin thickness. So this skin thickness of the wing in many actual designs can vary. So it can be different at different locations. So in such situations, whatever skin thickness you get at a particular location, you can mention what you're talking about. Or if you have data for almost the entire wing or a large section which is where it is varying, we'll take the largest of those skin thicknesses, the maximum skin thickness we will take and plot versus the gross weight. The next thing that we want is to, because once you plot this for all the 15 aircraft on the same graph, so you have those 15 points, so you will find that there are certain clusters which are occurring, especially if you have chosen a few of them of the similar type of aircraft. Then you would see that. I want you to comment why that clustering is happening, why at certain locations or close to that, why many more points are there, whereas certain regions where it's sparsely populated or there are no points at all. One, of course, people might not have considered designing those kinds of design parameters, but there could be a reason for it also, the physics behind it or the maths behind it. So I just want you to explore that option. Then I also want you to submit along with the soft copies of the references that you actually from which you have taken that information, so that the teaching assistants, when they are correcting it, they can make sure that the appropriate data is taken. Otherwise, it becomes very difficult to verify that. So this email, as I said, is only for clarifying doubts, etc. As usual, you continue to submit on Teams. So I will probably put up this slide on Teams so that you can just respond to that. Yeah. So the skin, as I said, the skin thickness data is difficult to obtain. So again, you can, because this is essentially a data sourcing that you're essentially doing, data mining, and some of you might have more sources to it, because other than the public sources, the web sources, Jane's All the Worlds and Flight Data International, some of you might have connects and things like that. So you could share this data, so no problem. Search, research, beg, borrow, but don't steal is what I said. Steal not from each other, that is fine, but stealing more from in the sense of using proprietary data of a company or something like that, which you might be privy to, and it's not supposed to be shared. So those kinds of things you be careful, not only from your own parent organizations, some of you are working in ISRO, etc., DRDO, etc. So some of the things that they might have worked with HAL and or a few other companies. So let's not use those kinds of data. For example, we've done a lot of projects with Boeing, Airbus, HAL, etc. So we've got certain data which is, we sign an NDA for it, non-disclosure agreement. So that is something that is private between the two parties. So let's not use those kinds of data, but whatever is publicly available and from other certain sources that are not confidential, we can utilize this data. Okay. Any questions on this assignment? Sure. Oh, I see. Okay, fine. That's fine. Let's make it 2 weeks. That should be fine, right? Yeah. So, yeah, today's Monday. So, not next Monday, Monday after that. Yeah. Okay, I think that's fine. Okay, I think I'll just rush through a little bit of this. I have to leave a little early because there's a comprehensive exam of a student that I have to attend. So the transverse members, once again, I think we mentioned this already. In the case of the fuselage, typically called as the frames and rings, and the same situation in the fuselage itself. It's covering most of the area or of very large cross sections. Then we typically call it as bulkheads. So these are the kind of skeletal images that you would find, a lot of them in Flight International magazines. And many other structural related magazines and things like that. So where you can actually see many of the things that we are talking about earlier. So all these stringers which are coming out, the transverse frames that are there close to an opening like this. For example, you have a much larger dimension for the cross section over there. So things like that, and where there need to be cutouts, the doublers that are there. Then for the, again, for the floor panel, to support the floor panel, what kind of supporting structure you have. Once again, because you want certain things to move around as well as to lightweight it, you want to have cutouts in them. So we were talking about even in the wing earlier, cutouts for fuels transfer to take place, the fuel lines to run through and the control lines to run through. But purely from a structural point of view also, we know that anything which is very close to the center anyway will not take much of the stress and strain. So why have that dead load over there? So even if there's no functional requirements, many a times you will find these cutouts just for light weighting to make the structure much lighter than otherwise. So I think, yeah, same thing in the case of the wings. So you see some actual examples of these transverse ribs, and you see those cutouts that we were talking about, which is over there, over here as well. And the spars, you could see the spars, the front spar and the rear spar, how these are essentially the web portion of that. Then you have the cap along with the skin coming on the top and the bottom. And the same thing in the case of the wings and the tails. There's a biological connotation to it called the ribs that are used in this particular case. Then some typical examples where you can see these rib-like structures. So in the case of the BAE, British Aerospace 146, which is an example of high cruise altitude passenger aircraft. And therefore there's internal pressurization once there are passengers. It's a higher altitude operation. So you typically have a circular fuselage cross section or close to circular in such cases to reduce the stresses that are there. You know that the hoop stresses will be the dominant ones over there, and certain manufacturing processes associated with the ribs over there. Okay. Now to compare and contrast that with another kind of aircraft, just to see how the design paradigms change a little bit. Now, instead of a large aircraft, you are having a small and light passenger aircraft. So you have a much simpler configuration as far as the structure is concerned, is only relatively speaking. So the spars, ribs, stringers, and the skin that is over here. And once again, you can recollect all those functions when you see these kinds of pictures in Flight Internationals. We were talking about what are the different things that each one of them does individually and as a team when they are combined with the rest of the structural elements. So you can actually explore those things. This is from de Havilland. And this is at a lower cruise altitude, and therefore there's no need for internal pressurization, even though it's a passenger aircraft. And therefore you see that in this case they could go with just a rectangular cross section, which could have probably been easier to fabricate, but just that the stress concentration, other things didn't matter too much over there because there's no internal pressurization. So and of course you know, when it's circular, as you go closer to the edges, the height drops down, so typically you could bang your head into it. So you want to, if it's a rectangular cross section, the ceiling is of the same height at all locations, and therefore it's much more comfortable. So where possible, you try to accommodate for these kinds of designs. And in between is what is being worked out in many of the current configurations, where you don't go for a circular or a rectangular, but more like an oval, which is stretched out more in one direction compared to the other, depending upon the layout design that you would like to have and the overall size of the aircraft. Okay, so this is another example. This is a case of a Harrier, and so here the fuselage, including the engine and the fuel tanks. So the cross-sectional shape is kind of predefined in this particular case. So in terms of the type of the aircraft, of course, you know that it's a vertical or short takeoff and landing kind of an aircraft. It's an attack aircraft. And so the kind of flight envelope it operates in is much more challenging compared to the previous two examples that we saw, which means that the loads would therefore be more, the stresses would be more. So you want to design it with more spars, and because you know that the overall sizing is limited by your aerodynamics and the functional requirements. So within that, how do you manage that? You might not be able to go for a bigger spar, but instead of that you might be able to go for more number of spars. So that's how you design based on case by case basis. Similarly, in terms of the ribs and skins, if you look at the spacing here, it might be much closer compared to what you had in the some of the less stressed examples that we saw, especially the previous one. So despite the complexity, the components functionality remains the same. When you say a spar, it's essentially taking the bending loads coming primarily from the lift distribution. When you say the rib, it's maintaining the cross-sectional shape, it's taking care of the buckling lengths, etc. And the skin is primarily taking the shear coming both from the torsion as well as the transverse loads due to the lift and or drag. So that is something that you have to remember. So the case by case basis is only going to change your quantification, but in terms of the design process, the how you go about the procedure, many of these things, both in terms of the terminology as well as the logical flow, is going to be the same. But of course, there are entirely different organizations, especially in India, dealing with the certification of these. They have quite different requirements. All of that has to be fulfilled. But nonetheless, purely from a structure point of view, where you're deciding on the materials, deciding on the different geometries, including shaping and sizing, many of these fall under a similar kind of physics and math. So that's what I want to emphasize over here. And in many cases, the terminology could also be same. The same aircraft industries who work on making both military and civilian aircraft. For example, Boeing makes both. So there are companies which make both, and therefore they have certain structural components, base structural components, which could also be certain platforms which could be interchangeably used. Then, concentrated loads coming from the landing gear is common for all three, but here you have additional loads not only from the landing gear and engine, but also from the arms that it is carrying. So obviously you have to take care of that, not only when it is there, but when it is released. So what kind of inertial loads come on the aircraft? Are you designing your structure to take care of that? So that becomes a very critical thing. So with the ammunition, being released and then the ammunition gone, there are three different conditions, and certain things might be more critical for certain components compared to the other. So you have to make sure you're designing for the most critical situation in all the cases that you have. What do I have here? Observe rib geometries change from the root to the tip. So you can see that the ribs that you have very different in terms of how they are as they go, not only in terms of the chords that they have. The airfoil cross section could also change, and many other requirements from a requirement point of view in terms of the lines that flow, etc., the control lines and or the fuel lines, etc. So based on that also the change could be there. Also you see certain locations there, it's not along the length, parallel to the length of the fuselage. There could be certain angles at which it is there. It could be due to many different reasons why many of these things are happening. Not all of them necessarily based on structural reasons. Okay. So any questions so far? Yeah. Coming again? Yes. Yes. Any particular reason you asked that question?
I think that is the arrestor hook at the end of the tail. Is it arrestor hook or
This one?
There's a tail, brake parachute.
This is, it's a brake parachute to essentially to reduce your landing runway distance.
But in case of carriers, they uses that short arresters for
Arrestor hook but it used to have a vertical takeoff. There are two ducts the side of the engine which used to provide vertical takeoff.
so just
below the wings.
Uh-huh.
They used to have two ducts where the engine
I see, this one you're talking about?
yes,
Yeah.
that is the engine.
Okay.
The thrust is to be directed downwards so that it could take off.
Okay. Because of the short and vertical takeoff that you want to have. Yeah.
Which is used while landing. And an aircraft carries a hook. It is carrier. Probably it is there for. I mean, when you land, it is there in most of the aircraft, but I don't remember if we landed at this.
Okay. So with that, we'll conclude today's class. I have to leave a little early. So meet on Friday.